So the normal distribution is a way of describing the probability of a particular event happening depending on the average value that a thing has and the standard deviation of that set. So if we were to use something pretty generic, like the width of your hand span, so if you were to measure from your pinky all the way to where your thumb lands and measure that value, mine happens to be about 18 centimeters. Now, if you were to think about people around you and you were to ask them to do that, some people's hands are larger than others, some people are smaller, but there is a range where you would expect to find people's hand size. So if, for example, you had someone show up and they could only do this and only get that far, so that measurement was only 6 centimeters, you would suspect you had a toddler on your hand, because that's not very large for an adult-sized hand. On the other side of things, if they were able to do this and reach 50 centimeters, those are some pretty big mitts in order to pull that off. So somewhere for human beings anyway, there is an average hand span, and if you can calculate an average based on a large data set, then you can calculate a standard deviation, and we can use those numbers to gauge what the probability is of finding someone with hands bigger than mine or hands smaller than mine based on an average and standard deviation for people. So if we were to try and graph that a little bit, we're going to make a bit of a histogram. So let's suppose that I'm a little bit average, that's the average, 18 centimeters. And suppose we allowed there to be a standard deviation of 3 centimeters, so that the average was 18 plus or minus 3. So if I went up 3, I would be at 21 centimeters. That's the average plus 1 standard deviation. If I went down 1, I would be at 15 centimeters. Let me fix that here so it's a little tidier. That's the average minus 1 standard deviation. Where am I getting these numbers from? Well, I'm hunting them and snatching them right out of the air to put on the board for you there. These aren't real data points, they're just for example. What did I say here? 18 is the average. Alright, now if I started counting people, right, I meet people on the street, the first person is probably close to average, the second person is close to average, maybe the next person is a little bit higher than average, maybe the next person is a little bit lower, then etc., etc., etc. And I start finding people. And I start adding them to my histogram. Now after a while, you might come across somebody with very large hands. Now I want you to think about how we were talking about outliers and typical range. When we were looking for a typical range of values, it was anything between the average minus 1 standard deviation and the average plus 1 standard deviation. These were your typical values here. Let me just pen that in for you. Typical. Then you had a space out here that was 2 standard deviations, and then a space out here that was 3 standard deviations. So what would that be? 18 plus 3 is 21, plus 3 is 24, plus 3 is 27. That there is the average plus 3 standard deviations, and that's where we decided that outliers were. So anyone with hands larger than 27 centimeters, and keep in mind, if that's 18, then this is 27, right? Like that's a huge hand. Anybody past that would be considered an outlier. So strange and with hands so big that we could actually consider them not belonging to the set of regular people. So as I'm building this graph out here, I'm going to start seeing lots of people who are in around the average. I'm going to see some people who are within the typical range. I'm going to see a few people who have big hands, but I'm not going to see many people out here. So if I were to keep doing this, keep asking people how big are your hands and measuring them, you see I'm starting to get a peak here around the average, because that's where most people are. Most people have average hands. That's sort of the way the definition works. And it kind of trails off as I go out here. Now if I did it on the same side, or on the other side, same thing, dropping by standard deviations, 18 minus 3 would be 15, minus 3 would be 12, minus 3 would be 9. Now 9 centimeters is that big. I mean, even my thumb is 9 centimeters long, so that's a pretty tiny hand. Same thing's going to start to happen on that end. That as your hand span gets smaller and smaller and smaller, there are fewer people out there. So there might be one here, there might be one here, maybe here. A couple people like this maybe. Keep interviewing people. There's a big one, then there's one like this, one like this, one like this, maybe like so. As I keep hunting for people, I'm getting more and more on the average value, with a few a little below average and a few a little above average. And as I get out into these extremes, past 1 standard deviation, past 2 standard deviations, up to my outlier boundary, I start to have vanishing numbers of people. Is there someone on planet Earth with a hand span of 35 centimeters? Maybe. Good luck finding them. But they may exist, but there's only one. 1 in 6 billion of us. So they're way out here. Their bar is not going to be very high. Same thing down here. Is there a person on planet Earth who's an adult and has a hand span that's only 4 centimeters long? Yes, there probably is. But again, good luck finding them. There's maybe 2 or 3 in the entire human population once you get down to a certain size, or up to a certain size. So I end up with this shape like this. And I don't know how many boxes I have on here, maybe 100. If I actually went out and asked all of the people on planet Earth to measure their hand span, there'd be 6 billion boxes in this. And so I'd have to start smoothing it out a little bit. And if I do that, I start getting a shape that looks like this. So the more common something is, the higher the graph is. That's how histograms and bar graphs work. So I have a nice peak around here, and I have a curve downwards out to this 1 standard deviation up and 1 standard deviation down. And then I have this rapidly declining appearance of values as I go up into the extreme ends this way and as I go into the extreme ends that way. Now, if you're into art, and I just sort of quickly draw you that shape and then draw a little circle underneath of it, put a little hook on top, and then maybe a clapper inside, maybe you see a bell. Depends on how forgiving you are with my artistic skills. So this thing here is frequently referred to as the bell curve. And what it's drawing for you is a quantity that fits a normal distribution. So a normal distribution is the probability of finding somebody with hand spans, or their height, or their weight, or anything else that you can measure, having a solid peak around the average, and then this rapid decline down to nothing as you reach 2 and 3 standard deviations up from that average. most things, well, I shouldn't say most things, there are many things in nature that follow this particular pattern. So it's really quite common in physics and chemistry and just statistics in general. If you're doing sociology, if there's a normal or an average, then things usually cluster around that average. And if they cluster this way, then we can use these locations, right, where they are in the standard deviation, in order to decide the probability of a particular event. So a little tongue-in-cheek here, the first question we're going to have to answer is it normal? So normal distributions, you have a bell curve here, and the peak of the bell curve lands on the average value. And this point of inflection, if you're taking calculus, you know what that is. This place right here where it stops curving this way and starts curving this way happens at one standard deviation above the average, and then there's a second one at one standard deviation below the average. So once you've got that shape up there, the first question you should ask yourself is this roughly symmetrical? There should be as many extremely large values as there are extremely low values. So I'm going to jot that down for you. Is it approximately symmetrical? The second thing you have to consider is how tightly squeezed this data is around the center. So within these two markings, this one standard deviation below the average and one standard deviation above, if it is a normally distributed data set, then you should have 2/3 of the data points falling within that range. Let me jot that down for you. 67%, that's 2/3 of the data falls within plus or minus one standard deviation. Now if I were to pop an axis on there for you, like so, and if I were to note that one standard deviation is about that wide, then two standard deviations would be about here. And here. Now the way this curve works, it has an asymptote as it goes down here, and again, if you're taking functions or grade 11 university math or calculus again, you'll know what an asymptote is. But as this steadily declines to 0, the frequency of this thing occurring is dropping to 0. That's what the graph is meaning. And so there's not a lot of data left out here once you fill in all of this. So by the time you get to within two standard deviations, two below, two above, you should end up with 95% of the data points. So 95% of the data falls within plus or minus 2 standard deviations. And if I were to go out one more standard deviation, remember here to here to here, you notice that I've hit the place where I'm almost right on the graph or right on the axis. My probability of finding something that far out has dropped to almost 0, and the same down here. So there was not very much data left before, there's almost none left now. By the time you get out to 3 standard deviations, 99% of the data should be between those boundaries. Falls within plus or minus 3 standard deviations. And this is why we were using 3 standard deviations as the outlier boundary in a data set. If 99% of the data points fall between here and here, that means there's only 1% left over, half of which is out here and half of which is down there. So if you found a data point that's more than 3 standard deviations above the average in a normally distributed set, then you are in the top 0.5% of objects within that set. Same if you are below 3 standard deviations, you're within the bottom 0.5%. So that's less than the first percentile, right? That's half of 1 percentile. So it's very uncommon for you to find something there. And if you do, then you've likely stumbled across that one person whose hand span is 50 centimeters wide. And if you're doing this data for a glove manufacturing company, and some person with a 50 centimeter hand span happens to land in your data set when you're deciding how big to make the gloves, you probably shouldn't use that person as your model. Otherwise, you're going to end up with gloves that are so large that most people could wear them as hats or pants. So you should be aware of that, and that's why we were using that boundary, because 99% of data points generally fall between 3 standard deviations below and 3 standard deviations above in a normally distributed set. So I have a data set here that is the height in inches of some people waiting in line somewhere for something. So the lowest point is 63 inches, that's 5'3", and then I have somebody who's 84 inches, which is 7 feet tall. I mean, that's curious that I have someone that big. But through the magic of being prepared in advance, I have an average value calculated for you already, which is 68, and a standard deviation of 6.78 inches. So I'm going to take a look at this data set, and I'm going to ask myself those 4 questions that we just did in order to decide if this is an approximately normal data set. So question 1 was, is it symmetrical? So I'm going to go through this, and I'm going to build myself a histogram. I set it up in advance for 1, 2, 3, 4, 5, 6 bins, the bin width being 3.5. So in my first bin, I have any data points between 63 and 66.5. That's the 63, 64, 65s, and 66s. So if I count them, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Second bin's between 66.5 and 70, so that does not include 70s, keep that in mind. So that will be my 67s, 68s, and 69s. So that's 1, 2, 3, 4 data points. Next bin would be including the 70s up to 73.5. So that's this one and this one. And then I need my 74s, 75s, and 76s, which don't have any. 82, 83, and 84 all fall in this bin. Alright, so question number 1. Is this symmetrical? No. So already on the first question we failed the test for a normal distribution. There's something funny happening here. For some reason there are many people on this end of the set, and then a handful of them that are very tall. So this is not appropriate to be modeled with a normal distribution. Just to go through and confirm that, we're going to check the other 3 questions because we already know it's not working. So I want to see what happens when I try those tests on something I know isn't right. So the next one was that 2/3 of the data has to fall within 1 standard deviation below and 1 standard deviation above. So I'm going to go and I'm going to check that. So the average value plus 1 standard deviation was 68 plus 6.78. So that ends up being 74.78. And the average minus the standard deviation ends up being This would be 61.22, I think. Let me just confirm. (68) minus 6.78, 61.22. Alright, so I'm just going to go and I'm going to count them. I'm going to find all the data points that are greater than 61.22 and less than 74.78. So that's this one all the way down, all the way up to 74.78. So that's these. So if I were to count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, that's 17 out of 20 data points. So 17 out of 20 gives me 85%, 0.85, which is 85%. Now I was only supposed to find 67%, but I ended up with 85%. So based on that particular number, there are too many in the center. There are not enough out in the wings. Second question you were supposed to check is how many are within 2 standard deviations and how many are below by 2 standard deviations. So if I were to test that, 68 plus 2 times 6.78 is 81.56. And if I go down 2 standard deviations, 68 minus 2 times 6.78, I get 54.44. So that's all of these data points, and even this one isn't that high. So I still have 17 out of 20 falling within that range, which is 85%. Now, from earlier, you were supposed to find 95% of data points falling between here, and I only have 85 of them. So not only were there too many bunched up in the center, there aren't enough in that middle range. And you can see right there in the picture, there's a big hole. If this was normally distributed, there wouldn't be a hole there. So that's problematic. Last test we have to check is for the outliers to see how many fall within the not an outlier range. So I have to check between 3 standard deviations. So 68 plus 3 times 6.78 gives me 88.34. And minus 3 standard deviations times 6.78 is 47.66. So 88 will catch all of these numbers, so I end up with 20 out of 20. That's 100%. That one's okay. I was expecting 99% and I got 100. That's pretty close. And with all of these, we're approximating a normal distribution anyway. So you'll never get exactly 99, exactly 95, and exactly 67. As long as you're within a reasonable approximation of those numbers, then you're okay. But if we were to look at this one, is it symmetrical? No. Are 2/3 of the data points within 1 standard deviation? No. 85% are. I needed 67. Are 95% within 2 standard deviations? No. Are 99% within 3 standard deviations? Well, kind of. But being kind of on to 1 of 4 categories is not enough to call this a normal distribution. So I would say with 100% certainty that this is not normally distributed. So I have a second data set here for us to test. This one is the handspan data. So how far is it from your thumb to the end of your pinky finger if it's fully extended, which I carefully measured from 20 individuals. So question 1, is it normal? So the first thing we're going to do is see if it's symmetrical. So I went and pre-chopped this up into 1, 2, 3, 4, 5, 6 bins. So the first one would be the 12s and the 13s. So there's 1, 2, 3, 4 of them. And then 13.7 to 15.3 would be the 14s and 15s. There's 1, 2, 3, 4, 5, 6, 7, 8 of them. 4, 5, 6, 7, 8. 15.3 to 17 would be my 16s, but not the 17s. So there are 1, 2, 3, 4 of those. (17 to 18.7 would be the 17s and the 18s, and there are 3 of them. And my last data point, the 22, well, that would be out here. So, question 1, is it symmetrical? No. I'm not even sure that it's better than the last one. You have this tag out here. I can see that this bar and these 2 bars are nice and symmetrical, and then I have some stragglers up here. So, is it symmetrical? Dot, dot, dot. Maybe? It's better than the last one. The last one had all the data points up at the front end and a trail afterwards. This one, there is some distribution around a middle value, but I'm not quite sure. So we're going to test the other 2 or other 3 questions about percentages of data points lying within certain standard deviations. So I did calculate an average of 15.3 on this set and a standard deviation of 2.22. Slide that back down there. So within one standard deviation, in the average plus or minus 1 standard deviation, 15.3 plus 2.22 would give me 17.52, and 15.3 minus a standard deviation, 2.22, is 13.08. So any data point between 13.08 and 17.52 is within 1 standard deviation. So if I go hunting for those, that would be the 14s through the 17s. So that's here and here. Yes, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 out of 14, 15, 16, 17, 18, 19, 20, which happens to be 65%. Now, we were hunting for 67. That's awfully close. Not exactly, but it's close. Next question was, within 2 standard deviations, so if I took the average, 15.3, and subtract 2 standard deviations, I end up with 10.86. if I add 2, 15.3 plus 2 times 2.22, I get 19.74. So that would be the 11s up to the 19s. So that extends to encompass all of these. Up to the 19s. And these ones as well. So that grabs 19 out of the 20 data points, which is 95%. Now that's exactly what we were hunting for. So that's encouraging. Last question. How many are within 3 standard deviations? So 3 standard deviations, 15.3, take away 3 standard deviations, gives me 8.64. And if I add 3, I get 21.96. So that would be anything between a 9, the 9s are in, and the 21, but not the 22. So this one then, that's an outlier. So I've managed to grab 19 out of the 20 data points. Give me 0.95. It's 95%. Now I was hoping for 99. Now, if you were actually trying to get an average size for human hands and a standard deviation for human hands, 20 people isn't enough. You notice that these percentages, 65, 95, 95, they're not exactly what I was hoping for, but they're close. One assumes that if I went and interviewed 200 people or 2,000 people, that these percentages would start to line up. So if I was asked, is there some evidence that this is a normal distribution, I would look at this shape and I'd say, is it symmetrical? Well, kind of. I see a peak, I see tails. And I'm after that shape like this. When you look at this, do you see a peak? Do you see tails? Sort of. So there's some evidence there. Is approximately 2/3 of the data within 1 standard deviation. Well, I got 65% instead of 67. That's close, so there's some evidence. Is 95% within 2? I got that exactly, so that's encouraging. Is 99% within 3 standard deviations? Not quite, but close. So there's a little bit of evidence. So in general, this set here, I would say there's enough evidence to allow us to treat it as a normal distribution. So the last one there was not, because these percentages were all crazy, and it was not symmetrical. It had a lead up on one side and a tail only over here. This one, I think we're pretty safe. So now that we've done that, we can actually do some calculations.